times big Y, right, plus big Y is equal to the Laplace transform of the unit step function of t minus pi over 2 of s plus the Laplace transform of e to the t times the unit step function of t minus 1. Now, if I was smarter, I would have done exactly the one I just did in example 7. Is it too late, or did I accidentally do it? All right, guys, we're going to make a small modification here to make our life easier. We're changing that 1 to a 3. Okay. Now we already know this. It's example 7. Woohoo! What's the Laplace transform of the unit step function, though? So notice that it's hard to see it, but if you look real careful, you can see that the constant function 1 is sitting right here, isn't it? So this would be equal to e to the minus pi s over 2, right, times the Laplace transform of 1 of s, right? Now, it's supposed to be the Laplace transform of 1 evaluated at t plus pi over 2, but you know what? The 1 is evaluated to 1 no matter where you are, so it's just 1. And so this is what? We just figured it was e to the minus 3s e to the third over s minus 1. Okay, fine. So we get e to the minus pi s over 2 times 1 over s plus e to the minus 3s times e to the 3 over s minus 1. This is all equal to s squared plus 1 times y. I'm starting to regret my life choices. This gives us y is equal to e to the minus pi s over 2 times 1 over s times s squared plus 1, all right, plus e to the minus 3s times e cubed over s minus 1 times s squared plus 1. All right. So now we just need to find the partial fractions decompositions of, and we could pull the e, let's keep the e to the 3 out front. Like, there's no need to have it in here. Let's put a 1 there, and let's stick that e to the 3 out here. Keep it out of the way. Yeah. So let me give these some names, and we can work on them separately. I think I'm going to use technology on these pieces. So let's call this thing here g of s, and let's call this character over here h of s, right? So g of s is equal to h of s is equal to, let's work out those. Did I forget to move the camera again? I think I did. Sorry, people at home. My bad. Oh, that's unfortunate. It's probably at the end of a video too. Oh well. Anyway, here we are. So let me get out my friend, the computer.
You should let moving the camera be someone's Caesar.
Moving the camera should be someone's Caesar. I used to just have students do it. But at some point, it stopped being helpful. I'm not sure why that happened. I think it has something to do with COVID. I still have some students do it. It's just, I don't know. It's a mix. Let's see here. There just doesn't happen to be anybody in here who sits in the back row and wants to, which is all fine. let's see here. So I'm just loading up Wolfram Alpha. And what I do there is I just type in, 1 divided by, I usually just use x times x squared plus 1. And then I'll write out partial fractions. And it probably will do it for us. Yeah, okay, this one was really simple. I probably should have just done it by myself. We'd be done with it by now. But it's 1 over x. In our case, 1 over s minus s over s squared plus 1. Okay, that's how that one works out. The other one, and there's nothing too mysterious here, guys. It would just take me about like 10 minutes of careful calculation to do these, and I don't want to hurry the other part, so I'm just doing this part with the computer. Anyway, so that one is 1 over 2 times s minus 1. Excuse me, that's, all right, that's fine. And then minus x plus 1. The minus is outside, okay? And then s squared plus 1.
X?
Yeah, there's an s. Sorry, my x's are showing here. We're good. So, and there's a 2. There's a 2 down here as well. All right. Okay, so the inverse Laplace transform of y of t is equal to g of t minus pi over 2, u of t minus pi over 2, plus e to the 3 times u of t minus 3, h of t minus 3. But we need to figure out what is the little g and what's the little h, right? But that's actually manifest from these up here. Like little g is the inverse Laplace transform of big G, right? And looking at this, it's going to be 1 minus cosine t. All right? 1 minus cosine t. And what's the inverse Laplace transform of h? Big H. 1/2 minus 1/2 cosine t minus 1/2 sine t. Taking the inverse Laplace transform. Now that I have those, and to be careful, this is exactly where I should really be careful. This is of t, this is of t, and we're talking about g of t. Like the of t here matters because we're going to do something other than of t right here, right? So of t matters quite a bit. So what we got is 1 minus the cosine of t minus pi over 2, all times the unit step function of t minus pi over 2, plus e to the power 3, u of t minus 3, all times big parentheses here, h of t minus 3, which is 1/2. 1/2 evaluates to t minus 3 real easy. And then minus 1/2 cosine of t minus 3, minus 1/2 the sine of t minus 3. And there you go. That's the solution to the differential equation subject to this discontinuous forcing function. That's how you do it. You have to, a couple different things. You got to take the Laplace transform of a function times the unit step function, and you also need to learn how to take the inverse Laplace transform in the presence of these exponentials, right? And it's a little bit tricky. It really centers around the boxed equation in the middle board, right? This thing here, the inverse Laplace transform of, the product of an exponential times g, we get back the unit step function times little g. Give you guys a chance to absorb this. Any questions? No questions? All right, so I mean, past here, of course, you'd like to see me do more examples with discontinuous functions, right? Because you just see me do like a couple. This is obviously like a slightly more, this takes some learning, okay? Like, it doesn't, people have to work on this for a little bit to get it. It's going to take you a few examples before you really absorb what's going on here. There is one other, like, there's a couple of other major technical things we can talk about. One of those is the fact that the inverse Laplace transform of the product of f of s and g of s is actually equal to the convolution of f and g. So that's an interesting one, convolution. So we'll probably talk about that one of the future classes. And then the other thing we need to talk about is the direct delta function, which is that function which is infinite at one point and yet has a finite integral. That you could use to model like a spike of voltage or a hammer hitting a nail, something like that. And so that's also very interesting and actually in some sense easier than this. But anyway, I think that's all I got for you guys today. So I will shut up. Enjoy your afternoon.